Fileviez Perez from Case Western University, and he's going to tell us about new gauge theories and the TeV scale. Pavel, please.
Okay, thank you so much. Just 1 second. Okay, can you see very well, right? Okay.
Yes, it is clear.
Before I start, I would like to thank the organizers of this very nice meeting. The program is actually fantastic. I'm very happy to talk here. As you can see, I will talk about gauge theories and the TeV scale. Before I even start, I would like to say that this presentation is based on my collaboration with my PhD student, Elio Golias, my student, Clara Murgi, that is starting a postdoc at Caltech, postdoc at UC Santa Cruz, postdoc in my group, Alexi Plasencia, and Mark Weiss from Caltech. Then, in particle physics, we have been thinking for a long time about this question. Is there a new physics at the TeV scale? As you know very well, in 2012, the Higgs boson was discovered, and we understand pretty well now how electroweak symmetry is broken, it's something real, nature. This is how the mechanism is playing a role in nature. And the standard model is a fantastic theory, right? And for a long time, we have been worrying about very, very many motivations to go to physics beyond the standard model. And then the model view today is that basically after the Higgs was discovered, we know that the Higgs is there. And we think about the standard model as a effective field theory that, you know, using just a symmetry to the standard model, in principle, we could write all the high dimensional operators that are allowed by the symmetries. Maybe some of them will be there or not. Today, many people mention the Weinberg operator, breaking lepton number. You can have the operators editing proton decays because they break a baryon and lepton number. And you could have any kind of a high dimensional operator, but of course, we don't know which one of them is there because we didn't discover physics beyond the standard model that allow us to establish the existence of these operators. And at least when I teach the standard model, I like to say to my students that, you know, the standard model has been there for a long time, but only after 2012, we know the Higgs is there. Then, you know, since 2012, we completed, let's say, the main features of the standard model. And to go beyond the standard model, the standard idea that we have been following is basically the sensitivity of the Higgs mass in the cutoff of the theory, right? The Higgs mass was discovered with mass 125 GeV. We don't really understand that number, but we understand that every time that we think about physics beyond the standard model, you know, the Higgs is actually, the Higgs mass is very sensitive to the cutoff. And this is the issue that we have been thinking for a long time. And this issue is the, let's say, the theoretical issue that have been driving the main ideas for physics beyond the standard model. I would say, in a nutshell, you could think about different scenarios that we have been thinking for a long time. You know that we have one of the best ideas that we have for physics beyond the standard model, I believe, is supersymmetry. And supersymmetry tell us that, you know, you can have a nice theory where the Higgs mass is protected, and you should expect a cutoff, you know, or the appearance of the supersymmetry particles around the TeV scale. This is, as you know, not very simple, because today, when you want to compute or predict the Higgs mass in supersymmetry, in the context of the minimal supersymmetry standard model, you actually have to do some efforts to be able to have live super partners and achieve the 125 GeV mass. But in reality, supersymmetry is the most elegant ideas that we have for physics beyond the standard model, where you can actually predict the upper bound for the Higgs mass at 3 level, and, you know, doing periodic correlation, you can achieve the Higgs mass that we see in the experiment. And this is one of the very best ideas that we have, and that is why it became so popular for so long. No? Second problem is that if the cutoff of the standard model is a very high scale, let's say any scale associated to lepton baryon number violation, or in this case, generically I'm thinking in a grand unified theory when you unify quarks and leptons, B and L are explicitly broken. And then if the cutoff of the standard model is just, let's say, a GATT theory, which has to live far, far away, that will be very painful because we have a huge fine tuning for the Higgs mass, but you know, maybe nature is like that and we have to live with that scenario. But this is a kind of a nightmare scenario because we cannot really test, we cannot build a collider to test a GATT theory, and then it will be really hard to even know what is going on. Then we should think that maybe something similar to supersymmetry maybe is there. And as you know, very exotic scenario, you think about large extra dimension or any idea that could achieve something like having a log cutoff, a log Planck scale cutoff, that could actually help a lot to, you know, not worry so much about the Higgs mass fine tuning problem because, you know, the Planck scale, fundamental Planck scale can be low. In reality, you know, all these scenarios suffer from many issues, but I would say if you follow the fact that you want to explain the issue about the Higgs mass, the sensitivity of the Higgs mass in the cutoff, and propose a new theory that will be much better than the standard model. These are the main scenarios that I consider appealing. The second one, of course, is a nightmare scenario where maybe we have to live with a fine-tuning issue. But so far, what we have in this community is that something similar to supersymmetry or supersymmetry should be maybe the answer. Okay, but we don't really know. All these ideas are just a speculation. The only thing that is true is the standard model. The rest are just a speculation that I hope that we will know in our lifetime. Now, in this talk, what I will do is something different. I would like to show you that even if you don't talk about the issue about the Higgs mass to motivate physics at the TeV scale, I would like to show you a set of theories, very simple gate theories, that they actually, to be consistent with cosmology and all the constraints that we have for particle physics, they should be around the TeV scale. Okay, this is a very strong statement. Basically, what I want to say is that if I consider some of these gate theories and I impose all the experimental constraints, including cosmological constraints, you expect that the theory could be at the TeV scale. Therefore, you could imagine that you could discover the theories. Okay, then these theories, they have a nice property. These symmetries are, of course, no anomaly free in the standard model. Therefore, to construct the theories, we need a new set to define anomaly free theory. And then you do the same thing that you do in the standard model. You do a spontaneous symmetry breaking and study all the consequences and the predictions. And therefore, you could think about how to test that in a consistent way. One nice thing about these theories is that in this new sector that you need to realize anomaly-free theory, one of the fields that is there is actually a dark matter candidate and will be automatically stable. Therefore, if you remember everything that we know about supersymmetry, many people like neutralino dark matter. I personally like too, but one has to be honest that in that context of the MSSA, one has to put by hand R parity to be able to have the stability of the neutralino. Here, this stability will be a consequence from symmetry breaking. And again, it's not a dark matter candidate that you will put by hand. It's something that is in the theory because you want to achieve anomaly cancellation in the simplest way. Therefore, at the same time, when you put all the cosmological constraints, you realize that this theory should be below the multi-TeV scale. Something also very nice about these theories is that you produce new CP violation. And therefore, we know very well that in the context of the standard model, we cannot do we cannot have a mechanism to explain the baryon symmetry in the universe. And these theories actually provide new CP evaluation to do the job for baryogenesis, which is something very, very welcome. And as I said, the dark matter is a bonus coming from the construction of the theory. The CP evaluation is also there as a bonus. And when you put everything together, you can show that there are actually interesting signatures for the Large Hadron Collider. I want to always emphasize the Large Hadron Collider is the best experiment that we have so far to make sure that we can discover new physics. And it's nice to see that these theories could be tested at the Large Hadron Collider. Okay. Now, before I go to a specific example, you could imagine, you know, many examples where you can that enters in this general classification. But I don't want to discuss any strange symmetry or anything like that. I want to take the standard model and think about what symmetries the standard model has. That also they play a huge role for cosmology. Okay, this is something very, very important, and because there are issues like baryogenesis and dark matter in cosmology that will be nice to have also an answer in the context of this theory. Okay. Then the first theory that you could think about that, the simplest one is just baryon number, okay? It's just baryon number, which is accidental global symmetry in the context of the standard model, only broken by SO2 instantons, 3 units. But it's a symmetry that we know that it is very important to understand the origin of the baryon number violation, because we want to study or have explanation for the baryon symmetry in the universe. Therefore, baryon number is a central symmetry in cosmology as well, okay? And then the general idea of considering baryon number as a local gauge symmetry was actually proposed by Abraham Pais in '73. It's an idea that never people pay so much attention. He actually never wrote any realistic theory or anything like that. But at least he mentioned that in a paper, but also Stringer, maybe according to him, also say something in a talk. But I will not go to the history. I just would like to show you, at least point out a few reference and a review where you can see realistic theories where this is actually realized, okay? Without going through if you want to see all the reference, you can go to this review. Then the idea is actually pretty simple. The idea is just take baryon number and assume that this is a local symmetry and you want to study the spontaneous breaking of this symmetry. This is already, as you can see, is also very important for cosmology because you will have the possibility to study the spontaneous breaking of baryon number, have control of that breaking. At the same time, let me emphasize, in any theory that we have for physics beyond the standard model, like the grand unified theory, we don't really understand, we have just explicit breaking of baryon number. We don't have the possibility to study the spontaneous breaking of baryon number. And this is a simple model where you can actually cancel all the anomalies. As you can imagine, you have to do here the same thing as you do in the standard model. You have to make sure that the theory is anomaly free, and then after that you can actually study the spontaneous breaking of the symmetry. Then you can go through this exercise and check all possible models. This is a very simple model that has only 4 extra representations, and it's enough to cancel all the anomalies. The whole theory is anomaly free, and the baryon number, which is the last number here, is predicted from anomaly cancellation. If you go through this exercise, you cannot put any charge that you want there. This is the simplest model that is predicting these charges. That allow you to cancel all the anomalies and you get this, okay? Then, of course, these fields, they have electric charge and they have to be heavy. You have to satisfy all the collider bounds. Then you just write down the whole Lagrangian. But since they have to be heavy, they have to get mass from a new symmetry breaking scale, which will be the U1B breaking scale. And for that reason, you have to introduce a new Higgs. But the important thing is that this new Higgs cannot have any baryon number random baryon number, the fact that the charges of these fields are fixed by anomaly cancellation, the only possibility that you have to have a large mass for these Higgses is that the baryon number is 3. Therefore, this is actually very interesting because means after symmetry breaking, you will get only possible delta B equal 3 operators. And the important thing is that this theory, in this theory, you never will get proton decay because to get proton decay, you have to break baryon number in 1 unit. And this is interesting because the fact, one of the main issues in theories like dry unified theory, where you are making a hard prediction for proton decay, this is actually good and at the same time bad because the scale has to be very far away from any thing that we can test. And this theory is actually a pretty simple theory that using a spontaneous symmetry breaking for baryon number is predicting that is stable. It's a gauge theory for proton stability. It's the minimal theory that you can write down that is anomaly free and be consistent with all the experimental constraints, and it's predicting the stability of the proton. You can see a similar idea in this paper. Now, before going to some of the predictions, I want to say that I want to emphasize that one of the multiplet that is there, when you check only for multiplet, the Liles one, that is neutral, is actually is automatically stable and it's a dark matter candidate. But again, let me emphasize this is a bonus that you get from the theory because you start thinking about the spontaneous breaking and doing anomaly cancellation and you get that. Of course, this model is predicting a new mediator for a new force that will be relevant for a standard model quartz and the new multiplet that are there for anomaly cancellation. This new theory will have a new Higgs that is the one associated to the symmetry breaking. And you could study all the decays of the Higgs and look for interesting signals like this. But the funny thing and interesting thing is that the dark matter, the fact that you have dark matter in the theory, basically this will define all the signals, the possible signals that you could have in these theories. And this is interesting because as you remember, if you think about supersymmetry, when R part is conserved, you have a lot of interesting signals with missing energy. Here you can have actually something very, very similar. And then the first things that you have to worry about is that it's important for me to understand what is the breaking scale for local baryon number. And then you go to CMS and Atlas, and you find they're actually doing an amazing job. You actually find that the mass of the new gauge boson associated to baryon number can be actually pretty light without assuming any small gauge coupling. Okay. For me, if I have to assume a tiny gauge coupling, this is not a gauge theory anymore because I never can see that. It's just putting by hand the parameter to 0. But the nice thing about these theories is that this is the only gauge theory that I know that can be around the letter V scale, and the gauge coupling has to be tiny. This means that there is a good chance to produce all these fields at the Large Hadron Collider and test the theory. Here, it doesn't make sense to go, let's say, below the letter V scale, because you have to think that the theory has also these new fields that are there to cancel anomaly, and they cannot be too light below the letter V scale because they have electric charge, and there are left bounds and there are LHC bounds that you have to satisfy. But it's nice to see that the theory could live around the letter V scale, below the TeV scale, without assuming any small coupling in the theory. Okay, and this is a nice thing is that you don't have to assume anything strange to satisfy the experimental bound. Now, since this is a great conference about the intersection between particle physics and cosmology, let me emphasize, here you just, in the beginning, start to think about a symmetry that is very important for baryogenesis, baryon number. Understanding the origin of baryon number violation is crucial to understand, to have a mechanism for baryogenesis. And as a bonus, you get the dark matter candidate there because you want to have anomaly-free theory to study the spontaneous breaking of the symmetry. And then if you check all the candidates that we have for dark matter, you know, the theoretical motivation, like neutralino dark matter, is, if you think seriously, is a little bit weak because our parity has to be imposed by hand. Even if you go beyond MSSA, we could discuss this issue. Typically, it's really hard to avoid our parity violation, but you know, of course, could be there. Now, let me talk a little bit about the dark matter candidate in this context. As I said, this is the simplest theory we have only the 4 representation. After the Higgs get a BEV, U1b actually is broken to a C2. And this is the symmetry that is protecting the dark matter candidate. And the Lilas field will be the dark matter candidate. And basically, this particular theory is predicting a Majorana fermion that I call here leptophobia in the sense because the annihilation channels to lepton will be suppressed, but they will use you have the mediators, the leptophobia gauge boson playing a main role for annihilation. And then it's just a Majorana fermion that, you know, talk to the CV, the U1b gauge boson, the U1b boson talk only to quarks and the standard model quarks. And of course, you know, you can write the new Higgs, the physical, they mix the two, the standard model Higgs and the new Higgs, they mix, and you can write all possible interactions. But the important thing is that the minimal theory is predicting that the dark matter is Majorana, is automatically stable, and as I emphasize again, it's actually a bonus, no? And therefore, you can now do the simple analysis that you do in many models for dark matter. You just study the possibility to achieve the dark matter Rayleigh density that we need in cosmology. And you know, in this case, you will take all the annihilation channels and do solve the Boltzmann equation, and you will find something like that. Basically, this is in the plane, the mass of the gauge boson, the dark matter mass. You can actually have different channels. Here in color, you will see which are the main channels in this parameter space. For example, here, you will get that the CV and the second Higgs annihilation to this field. You basically will find this region of parameter space. This is the main annihilation channel, choosing these particular parameters, values for the parameters. Choosing GB.1, you are automatically satisfy all the collider bounds for the leptophobia gauge boson. And something very interesting here, and this is why it's important to have a theory for dark matter and not a simplified model, is this line here that you find here is actually the dark matter is getting the mass from the same symmetry breaking scale. And then when you are increasing the dark matter mass, due to the fact that you are having a well-defined mass for the gauge boson, you will have to face the issues that the Yukawa coupling for the dark matter could become non-perturbative if you keep increasing the Higgs mass. And this is why this area below this red line is actually excluded by perturbativity. And then the theory, if you want to be consistent with cosmology for this particular input parameter, you have to live below, let's say, 20 TeV or something like that. Clearly, the theory cannot live at any scale, okay? Then this is a very important thing, which is a feature of many dark matter candidates. But here, the point is that you have, as a prediction, this theory, the dark matter candidate is actually predicted from anomaly cancellation, and these cosmological bounds are predicting that the mass, which of the leptophobia gauge boson, which is basically the let's say the U1 breaking scale, U1b breaking scale, cannot be too heavy. Okay, if not, you will overclose the universe. And you can actually do a more general exercise. You can actually take and think about changing all the parameters in the theory and pushing the gauge boson even to the limit of no perturbativity. And here, when I say the limit of no perturbativity, you have to check all the couplings in the theory and make sure that you don't break perturbativity in any of the interactions that you have in the theory. And then again, it doesn't matter you do, this is a nice exercise to really check which is the let's say, kind of absolute upper bound. But here, for this value of the gauge coupling, you can see the upper bound is around 27 TeV or something like that. But of course, the theory doesn't need to live at that scale, okay? Because I am showing a extreme case where you just pushing the whole mass of the gauge boson to very large value, where even no perturbativity perturbativity will break down. Then generically, this theory will have to live below that scale. And this is actually very, very, very important because the U1 breaking scale has to be low, below the multi-TeV scale.
5 more minutes.
Thank you. And then, of course, you can check direct detection experiments. There is no any issue in direct detection experiment. And then let me emphasize that the very important thing is that you try to understand the spontaneous breaking bar number, which is crucial for cosmology, and all the fields in the theory, they are getting mass from the same symmetry breaking scale. And the fact that cosmology tells you that the scale cannot be too large, all these fields, they have to live below the multi-TeV scale. Therefore, you can actually think about, for example, the Higgs, the new Higgs, how to test this at the collider, the LHC. And you can do a very nice exercise because this model has only a few parameters. Therefore, once you want to fix Rayleigh density, you can predict even the branching relation for the Higgs in different dark matter, in different scenarios where the different annihilation channels are very important. If you study the Higgs to gamma gamma, you have to think that all the new fields in the theory, they will contribute, and you can do the full exercise. And I will show you something interesting is that, for example, this is one scenario where the branching relation to gamma gamma can be actually pretty large. When I say pretty large, means con respect to the standard model. When the standard model is just is around 10 to the minus 3, here the branching relation could be actually very large. And also the decay to dark matter could have the branching relation could have a huge value. And at the same time, you could think about other scenarios, which I personally like more, the scenario where you don't have to rely on any resonance, you have only this particular annihilation channel. You can find something very similar that the branching relation to gamma gamma is actually very, very large. And this is very important for example, to study the production of the Higgs at the Large Hadron Collider. Generically speaking, this Higgs, the new Higgs, will mix on the standard model Higgs, and as you know, there is a bound on the mixing angle coming from when we try to use all the constraints coming from the Higgs property, the standard model Higgs property. This theory provides a new channel which doesn't need to be suppressed because this new gauge boson can be very light, and then you can have associated production of the Higgs with the CV. These are the prediction, and the excluded values are there. And then you can imagine, for example, channels like this where the CV can decay to TT bar and the Higgs can decay to gamma gamma, and you do the full exercise with large luminosity. You can see that if the CV is light below 500 GeV, you can have a large number of events for these channels, which is good. Then one of the things that we like to emphasize, even if I don't have the time to explain, is that this theory is actually even more interesting because when I take the fields that are needed to define anomaly-free theory for U1b, you can see that U1L, the total electron number, can be also anomaly-free in the theory. Therefore, this is very, very important for baryogenesis because means you have a theory where you have pure control of the initial condition for baryon electron asymmetries. When the symmetries are there, you cannot have an initial condition that tell you that there is a primordial baryon asymmetry or primordial electron asymmetry. Therefore, in this case, you can have here basically is a discussion about having leptogenesis at the highest scale when U1L is broken. You can have leptogenesis therefore, I don't have time to talk about all the different models, but basically there are mainly two classes models. One is predicting Majorana mass, and the other is Majorana mass for the dark matter or a Dirac dark matter. If you have the case of Majorana, the mechanism is pretty simple. Basically, you can have leptogenesis at the high scale, and the Falloran conditions are different due to the fact that U1b can be broken at the low scale. And then the Falloran conditions are different. You can go through the chemical equilibrium equations and check how the lepton asymmetry translates to the baryon asymmetry. In the other models where you have a Dirac dark matter, it's actually even more exciting because the same right-hand neutrino that gives you leptogenesis can actually generate a dark matter asymmetry in the theory. And you can put everything together and classify the different mechanisms. This is what we have here. But let me emphasize, this theory gives you the possibility to really have control of which are the primordial symmetries in the theory, and study the spontaneous breaking U1b at the low scale. In this case, U1L is broken at the high scale. Then before I finish, I would like to say that I focus mainly on this simple model because I think it's always good to have the simplest possible model to transmit the idea and everybody can really understand. You can do things that are a little bit more exotic, is that you can think about how to get U1b, for example, from a granulified theory or from a no-billion gauge group, okay? And then it's nice to see, for example, you can go through this exercise that you can actually unify QCD when U1b in SO4 theory, where you know the quarks are unified with the new fields dimension that are there for anomaly cancellation. And this is a nice exercise that tells you that this is actually very important to go and think about implication for all ideas that we had from granularification. No? Then I would like to summarize my talk in this way. As I mentioned in the very beginning, I still believe that supersymmetry is one of the very best ideas that we have, in particular that provide a nice understanding how we can compute the Higgs mass. We don't know if something like that is there. Anything that I say here is consistent. You could think about thinking about awesome supersymmetry theory with this feature, but I don't really want to go there. I just want to emphasize that it is possible to write very simple theories where the symmetries that we have there, the new gauge symmetries that we have there, are crucial for cosmology. And in particular, I only had time to speak about the possibility to study the spontaneous breaking baryon number. Clearly, the spontaneous breaking baryon number is very interesting for baryogenesis. And here, the fact that you are predicting a dark matter candidate, you find that the theory has to live below the multi-TeV scale. Then, and in particular, I mentioned to you again, the minimal theory predict proton stability, means this is a very interesting prediction. And I emphasize the cold dark matter candidate for anomaly cancellation is a bonus, that's something that you don't expect, because if you find that the minimal theory doesn't predict any dark matter candidate, that could be, you have to live with that. And the fact that the scale has to be low, you can actually look for this new Higgs that has information about how the symmetry was broken, study the case, the production channels. In this case, it's interesting to see you can have a large production relation to photons or dark matter, and then you can study the different signature at the Large Hadron Collider. Then the same theory can be used to gauge total lepton number. Therefore, you can have a really unique framework to understand the baryon asymmetry in the universe, because you can be completely sure that there are no any primordial baryon or lepton asymmetries, and then you study everything for spontaneous symmetry breaking. You can use leptogenesis, you can use a different mechanism. In this case, the paper that I mentioned, we study leptogenesis to even explain, will have even the possibility to have a dark matter asymmetry. And again, my main goal for this talk was to emphasize that we have to be careful with the fact that typically we follow only these dogmas that we have in the community, like supersymmetry and other theories, because we believe that the Higgs mass is very important. I also believe that the Higgs mass is very, very important. But here I show you that studying gauge theories for symmetries that are crucial for cosmology, once you put all the cosmological constraints, this theory should be below the multi-TeV scale. Therefore, there is a way or maybe we will know about these theories soon, because you can actually test at the Large Hadron Collider. Okay,
Thanks
thank you so
very
much.
much, Pavel. We are a little bit over time, but I see a couple of questions on Q&A. Maybe we'll address one of it. And Amber Rope asked the following question. Could you elaborate on the unique collider signatures that arise from by adding these new particles?